Welcome to this lecture, which is on the space science, and it is going to be a very basic introductory level of lecture. And when we speak about space, the first question that comes to our mind is, what is space? And let me tell you, at this moment, there is no universally accepted definition of space. While there are various definitions of space existing, and there are various understandings about the space in different contexts. So when you speak about different treaties, say International Space Treaty or Outer Space Treaty, which has been signed by several countries, it defines outer space as an area which is beyond the Earth atmosphere, but it doesn't specify any number that from these kilometers onward the space starts. And there are different national definitions also, which are given by some countries. And there also have been certain scientific definitions based on certain phenomena which happen. One such example is that whenever you are speaking about flying an aeroplane and or flying a satellite, the physics is different, and this demarcates two zones. One zone is known as the zone of aeronautics, wherein the aeroplanes fly, and there is another zone which is above that zone, which is known as the zone of astronautics, where aeroplanes don't fly, but the satellites are placed in those regions. In the picture, you are able to see Theodore von Karman, a renowned aeronautical engineer and scientist who has had significant contributions in the domain of aeronautical engineering. He has come with a concept of an imaginary line which is about 100 kilometers above the mean sea level of the Earth. And this line is known as the Karman line, which is shown by the dotted line in this picture. So this line, he mentioned, puts distinguish between the zones of aeronautics, which is below 100 kilometers, and the zone of astronautics, which is above 100 kilometers. And if you see, in terms of the atmosphere, amount of atmosphere which is present, you imagine a volume of dimension of 1 meter cube right on the surface of the mean sea level. It will weigh around 1.1 kilogram. That is 1.1 kilogram of atoms and molecules are present in a volume which is 1 meter cube on the surface of the Earth. But when you are going to weigh the same amount of volume of air at 100 kilometers altitude, that is at the Karman line, it is around 10 to the power minus 7 kilogram of atoms and molecules. So you can see how much tapered is the atmosphere when you are going above and above the mean sea level. And very slowly, the atmosphere of the Earth merges with the interplanetary medium. And that is how the Karman line concept has come. But let me tell you here, although the Karman line is one of the ways to look at the problem of what is space, there are several interesting aspects of space science which happen well below the Karman line and above the Karman line. If you see the left-hand side panel of this slide, you are able to see here temperature is plotted in the x-axis and altitude is plotted in the y-axis. And you are able to see how temperatures vary with altitude on Earth. Say at a given location, there will be some altitude where the temperature will decrease with altitude, and then there will be an increase in the temperature. So basically, it shows the structure of temperature variation over altitude. And this is the basis of stratifying the atmosphere of the Earth. We are familiar with the terms troposphere, stratosphere, mesosphere, thermosphere, and over and above that, we are having exosphere, wherein you have less number of atoms and molecules per unit volume, and it is almost nothing present. Now, you are able to see where does Karman line lie in this graph. So below the Karman line, you have got good structures of temperature, which is a matter of interest to the space scientists who work in the realm of Earth's near atmosphere. And if you see the right-hand side picture, you are able to see what happens when the solar radiation, especially the ultraviolet and extreme ultraviolet radiation from the sun, interacts with the neutral atmosphere of the Earth. There are ionization happening of a fraction of the neutrals, and thus ionosphere are formed. And ionosphere also is formed in multiple layers. I have shown here in the day side D region, E region, F region, which are all different layers of the ionosphere. If you see what happens in the night side, certain layers merge and the number of ionospheric layers are very less. So this is also a very interesting phenomena which keeps the scientists engaged to understand what will happen in terms of the interaction between the sun and the earth. And you see the common line here, well below the common line and above the common line, everything is interesting for the space scientists. So where does the space start? Not necessarily it has to be 100 kilometers. It all depends on what aspect of space science you want to study. Now, after having said this, let me tell you, we all know that the sun is the primary driver of everything in the solar system. Sun is the source of energy of every process. Every process requires energy to happen, and sun provides that energy. If you see the cartoon, which is on the left-hand side, you will be able to see sun is comprising multiple layers. The innermost part of the sun is the sun's core, wherein the nuclear fusion happens. And you know, in the nuclear fusion, the hydrogen atoms, they are fused and helium is formed. And because of this process, there is some unaccountable mass we call mass defect that is manifested as the energy by the famous mass energy equivalence, which was given by Albert Einstein. And this energy, which is mostly coming out in the form of the gamma rays, they are traveling to different layers of the sun, and eventually what we see out of the sun, a good part of that is the visible light, which our eyes can appreciate, our eyes can sense. So there are a lot of processes which happen when the photons of the gamma ray have the transition from the core to the outermost layer of the sun. And what all things happen? If you see the different layers of the sun, right after the core, you're having radiative zone of the sun, wherein the gamma radiation gets absorbed and released repeatedly by the solar material. And you know what is the solar material? It is the plasma, the fourth state of matter, and which may take millions of years to cross this radiative zone, which means today, whatever you're seeing as sunlight, after having left the sun's surface, it has taken only 8 minutes to reach your eyes. But the gamma radiation, which has been the reason for the visible light which you are seeing on the surface of the sun today, it has taken a few million years to have come out of the core of the sun. Multiple times it has undergone travels in the radiative zone. Then it went to the convective zone, wherein there have been lots of processes by which the photon energy got degraded here by driving the process of convection of the solar material, which I have tried depicting with some dotted circular loops. Okay, and if you see the entire sphere of the sun, which will be of the radius of around 7 lakh kilometers. But if it is possible for you to peel the skin of the sun, and you are going to see this part zoomed, at the outermost layer, around 2000 kilometers thickness, you are having photosphere and then chromosphere, and then you're having one line which is known as the transition region. This transition region is around 100 kilometers thick, which is nothing. If you see how big is sun is around 7 lakh kilometers. So after this transition region, there is a very high rise in the temperature of the solar material, and that's how we see the solar corona, which is the atmosphere of the sun, which is extended to almost the entire heliosphere, which is very hot, which is very close to the sun, and its temperature has a sudden jump. I am not going to that discussion. So here I have drawn attention at another line here, which demarcates the radiative zone and the convective zone. In between these two zones, I have shown one dotted line, which is known as the tacho line. And the tachocline concept is also very important because tachocline acts as a transition zone between the radiative zone and the convective zone. It is a region where there is a significant change in the sun's rotation. You know, the sun is also rotating like Earth, but there is a difference between how the sun rotates and how Earth rotates. So what actually happens, let us see. The radiative zone rotates more like a solid body. So up to this, the rotation of sun is more like a solid body. But what happens in the convective zone, that is outside the tachocline? The convection zone rotates differentially, that is, at different latitudes, the rotation rate is different, which is not the case like the Earth, because Earth is a rigid body, solid body. But in Sun, which is a ball of plasma, this kind of differential rotation happens, and you will be, many of you are aware that the equatorial region of the Sun rotates faster than the polar region of the Sun, and that is why there is a special spiral structure which comes out of the sun's magnetic field. So let us see how does the sun's magnetic field look when it comes out of the spiraling sun, and that this rotation is also happening at different rotation rates at different latitudes. But let me tell you here one more fact which you will be able to appreciate if you are remembering your lessons in physics. Sun is a ball of plasma, and plasma is nothing but a collection of charged particles. Now, when these charged particles are in motion, they generate magnetic field. And as a collective whole, the sun also has lots of crisscrossing magnetic field, and there are certain instabilities in the solar plasma, which is manifested in terms of certain processes like emission of charged particles from the solar ball. And as the charged particles are emitted from the solar plasma, it is associated with the motion of this charged particle is associated with a magnetic field. And this differential rotation of the sun gives rise to a peculiar geometry of this magnetic field, which is known as the Parker spiral, which you can see in the right hand side of this slide. You see, if you are seeing from the sun, stop. Suppose you are looking at the sun's, say, North Pole, and you will be able to see different orbits. Suppose this blue one is the Earth's orbit, red one is the Martian orbit, this brown color is the orbit of the Jupiter, and in between you're having the spiral magnetic field lines. And in the next slide, I'm going to show, if you are imagining some charged particles coming out and they're following this magnetic field, how they're following this magnetic field, that will be coming in the next slide. So let us have a look at that. So this is sun, and you're able to see there are certain things which are coming out of sun. I will tell what are these which are coming out of the sun. But for the time being, let us concentrate on this yellow spirals. You know what are these yellow spirals? They are the trajectories of the charged particles which are coming out of the sun. They follow this spiral, Parker spiral magnetic fields overall, and their individual motion is like a spiral. So they are following the magnetic field lines in spiral trajectory. Now the question is, what are the effects which come out of the sun? If I ask you this question, the first answer which you will come up with is the sun is affecting the earth by its gravitational pull. Yes, very much correct. Apart from the gravitational pull, the next point you are going to tell about the sunlight. Yes, sunlight is very much an effect from the sun which is coming to the earth. So if I have to speak in a more general sense, I will not say sunlight, I will say solar radiation, because sun not only emits the visible part of the electromagnetic spectrum, but sun also emits a significant power which is in the higher energy domain, which is comprising the ultraviolet and X-ray radiation, and also the lower energy regime, which is infrared and radio waves. So that's radiation. But sun is not all about gravitation and radiation. Sun is also about particles and heat. When we come to particles, I want to mention what I have just mentioned previously. Some charged particles, they are mostly ionized hydrogen and doubly ionized helium. and a small fraction of heavier atoms which are ionized, they come out of the sun and they get spread in the heliosphere. Out of this, around 95% is the ionized hydrogen. Around 4 point something, less than 5%, they account for the ionized, doubly ionized helium. And the remaining fraction of the totality, they account for the heavier ions which come out of the sun. And these charged particles are also accompanied by electrons, because charge neutrality also has to be satisfied. And this is called the solar wind. And it is a continuous process. If you see an animation, the animation will be shown like this. Their sun is there, and continuously there is a granular motion of something which is being emitted from the sun. And we call this a solar wind. This is a continuous process. But apart from this, there is a few more things. With each solar wind particle, a charged particle, there is an associated magnetic field effect, which I have shown you already, which I have discussed. Whenever I have written field, it is the magnetic field, which is also termed as the interplanetary magnetic field, IMF, or the solar magnetic field. So this is not the entirety. There are other things to speak about the sun. There is a process which is known as the coronal mass ejection. Coronal mass ejection is a process where sometimes a chunk of the solar material comes out because of certain instabilities within the solar plasma, and they are lost to space. And this, a chunk of mass coming out of the sun, is known as the coronal mass ejection, or CME. Apart from this CME, there is another process which is known as the solar flare. Solar flare phenomena is a phenomena of sudden brightening up of certain spots on the sun. Not sunspots, don't confuse with sunspots, because sunspots are dark regions, which are colder regions, temperature-wise, energy-wise. I'm not speaking about the sunspots. I'm speaking about certain regions of the sun, due to some reason, becoming very bright, and that we call the solar flare, as if somebody is sitting on the sun and taking a flash lamp camera and taking pictures. And that kind of a flare may not be in the visible region. It could be in the ultraviolet or the X-ray region in the solar spectrum. So if you have an imager or a camera which can see the sun's ultraviolet part of the radiation or the X-ray part of the radiation, you will be able to see some sporadic flaring up of certain regions of the sun, which we call the solar flare, and which is basically the photons, high energy photons coming out of the sun. Coronal mass ejection was different. It was mass coming out of the sun. Now, after having said this, let me tell you, quite intuitively, you will be able to appreciate with these kinds of effects, its radiation, its solar wind, its magnetic field, its coronal mass ejection, its solar flares, so many things, sun affects different planets and different natural satellites and every other member of the solar system. Had there been no other members in the solar system, had sun been only with a single member in the solar system family, it would have gone out of the sun. But imagine you are embedding different planets, natural satellites, and other solar system bodies, and they're becoming obstacles to this continuous or sporadic flow of different entities which are coming out of the sun. Depending on the type of the obstacle, here the obstacle means either the planet or a natural satellite, whatever, the nature of the interaction also varies. The objects can be in the solar system can be classified in a number of ways. One way to classify is whether it has atmosphere or it doesn't have any atmosphere. Another way of classifying is whether that object has an intrinsic or dipole magnetic field or it doesn't have one. So I have tried preparing a matrix with these two parameters, like with atmosphere, without atmosphere, with magnetic field, a dipole magnetic field, and without a dipole magnetic field. And in this slide, I have tried to elaborate on what kind of interactions happen in those kinds of celestial bodies in the solar system. As for example, I have written for the Earth, what are the kinds of phenomena happen. You see here, I have written about aurora. I have written about Mercury. Mercury is different because it is without atmosphere but with a magnetic field. Again, Mars is different because Mars is having some atmosphere, not as thick as Earth, but it is without a dipole magnetic field. But Mars has something else. Mars has a part of its neutral atmosphere converted to ionosphere. And when this ionosphere responds to the solar magnetic field, it experiences an induction effect. Those who remember your early physics classes, this Maxwell's equations and Faraday's laws of induction, you will be able to appreciate that how a field and the charged particle interaction can induce a secondary field. Exactly same thing happens in Mars. So we say Mars doesn't have a dipole magnetic field or intrinsic magnetic field. We say Mars has a induced magnetic field. But when it comes to the Earth's moon, it doesn't have any atmosphere. It doesn't have a dipole magnetic field, but it has got some patches of magnetic anomalies. We will not go to that discussion right at this moment. All that I wanted to say is that the planets are different, the natural satellites are different in terms of many parameters, and Sun interacts with them differently because of their differences. And let us take, in this context, the example of the Earth, our own planet. Earth, if you see, there is a region where in the interior of the Earth, Earth's mantle, there is dynamics of the molten lava, which comprises charged particles, and the dynamics of these charged particles has given rise to an overall magnetic field of the Earth. It is equivalent to as if there is a bar magnet which is buried inside the Earth with its south pole almost towards the geographical north and its north pole pointing almost towards the geographical south. But it is not the case. It is not the case that you go on digging the soil and you are going to encounter a bar magnet. It is not the case. It is effectively working as a bar magnet. What is effectively working as a bar magnet? The molten lava, which is inside the Earth, the motion of the charged particles, which we call the geodynamo, that is giving rise to the magnetic field, which is equivalent to as if a bar magnet is present. And you see a certain kind of similarity here. Here also I'm speaking about some motion of the charged particles giving rise to a magnetic field of the Earth. Similar thing I spoke about when I was speaking about the Sun's magnetic field. There also I spoke Sun is a ball of plasma. Plasma is nothing but a collection of charged particles with certain conditions met. And these charged particles, when they're in motion, they would generate magnetic field. Now, there is Sun, there is Earth, and Sun is also giving some magnetic field. Earth is also having its own magnetic field. And now in space, when these two magnetic fields interact, let us see what happens. Let us follow this animation. Sun is in the left-hand side, and you see the solar wind particles which are appearing like smoke, which are not smoke, which are basically solar wind. And these blue lines represent the magnetic field lines of the Earth. What you can see here, there have been lots of reconnections or rearrangements of the Earth's magnetic field lines. Let me play the video once again for you to understand or appreciate better. See, it is the Earth's magnetic field is tapered in the anti-sun side, and there is a rearrangement of the magnetic field of the Earth happening. Sometimes there is a connection happening, we call this reconnection. And when this happens, some particles come and hit back the Earth. Okay, and because of these kinds of phenomena, particles hitting back the Earth, or wherever the magnetic field of the Earth is bit weak, direct deposition of the solar wind, they cause some other effects, which I'm going to show you here. Many of you have guessed correctly. This is aurora. Yes, I was about to speak about the aurora. Aurora borealis and aurora australis, which you are very much familiar with from your geography lessons. So aurora borealis is the one which we see in the northern high latitudes, and the aurora australis is the aurora which we see in the southern high latitudes. And if you see what is happening in the sun, you'll be able to see two things. One is that continuously there is a stream which is flowing from the sun and coming from the left to the right. This is the continuous flow of the solar wind. And you see how the solar wind is getting deflected by the Earth's magnetic field. And some of this is getting deposited to the polar regions, giving rise to the aurora, as I have shown here. But apart from this continuous granular motion of the solar wind, there is also something which is sporadic. Sporadic means it is not happening continuously, it is happening all of a sudden. And this all of a sudden happening phenomena, they include this coronal mass ejection and these solar flares. And this region is sometimes the space scientists call the near Earth space, although the near Earth space is again another term, like the term space doesn't have any universally accepted boundary. Similarly, the term near Earth space also doesn't have any universally accepted definition as of now. The people who are working on space debris, they define the region where space debris become threat to the Earth. They call that space near Earth space. There are people who are working on the satellite technology. They are very much bothered about if any solar flare or coronal mass ejection event affect the satellite. And that region, which are vulnerable to get affected, satellites are also present, they tend to say that is the near Earth space. And the people who are studying the Sun-Earth connection, these are all the connection between the Sun and Earth, right? They tend to say the region between the space between the Sun and the Earth is also near Earth space. So it all depends on the perspective, on the scientific problem you would like to address. Now, these discussions have been in the context of the solar system. And why do we have to understand the solar system? Since solar system is all about the science of the sun, the planets, and the natural satellite, science of the comets, asteroids, and dust, and also sun's effect on the solar system members. And once we understand this, we can translate our knowledge to the other solar systems. Not necessarily our solar system is the only solar system. There could be other solar systems, other suns, other planets revolving around that solar system's host star. In order to understand that system, let us understand our system better. So that is the prime motivation to understand our solar system. And here you will be able to appreciate a very interesting aspect of this entire science. See, the solar system was formed around 4.5 billion years ago from a dense cloud of interstellar gas and dust. And the cloud all of a sudden started collapsing. How did the cloud start collapsing? That again is a matter of several theories and several conjectures. People say that one possibility is that there was a shock wave of a nearby supernova which was exploding, and that shock wave disturbed the stability of this interstellar gas or dust. And then because of this triggering mechanism, the gravitational pull of this interstellar dust and gas molecules, they took over and it started collapsing. And when they collapsed, they formed the solar nebula. And the solar nebula was a spinning, swirling disk of material. Now, this all happened 4.5 billion years ago. Now, out of this, the entire material, without going to the details of the evolution of the solar system, let me tell you, around majority, around 99% of the mass of this interstellar gas or dust has been used up to make the sun only. The rest, whatever was remaining, majority has gone to make the giant planets like Jupiter, Saturn. Whatever remains constituted the other giant planets, terrestrial planets, natural satellites, and other small comets, asteroids, whatever things we have today. Now, you have to appreciate the building blocks were same 4.5 billion years ago. Evolution happened, solar system formed. Still, why the members of the solar system are so much different? Today, when you see, there is a distinct difference between Mercury, Venus, Earth, Moon, Mars, Jupiter, Saturn, Uranus, Neptune in terms of several parameters. Here I have mentioned about only the magnetic field and the atmosphere. But there are differences in terms of atmospheric composition. There are differences about their orbits. There are differences about their spin, about their own axis, the tilt of the spin axis. So how they are different, despite the fact that they have started all together, uh, but today they are not comparable. We do some comparison between the Earth and the Venus, in some aspect Earth and the Mars, but differences are more than the similarities. These differences has started or initiated a branch of study which is known as comparative planetology, where you compare the different attributes of planets or the planetary bodies, not necessarily planets, planetary bodies in general, and you start finding the reasons why they're different, how did they evolve, how the way of evolution was different uh, from one celestial body to the other. Now, if you see the members of the solar system, there are terrestrial planets, giant planets, and there are interplanetary dust, there are natural satellites, minor planets, ring systems of the giant planets, comets. So you must be having that, whether all the giant planets have got ring systems. Yes. Although in our regular school textbooks, we show the ring of only Saturn, but it is not correct. It is only a matter of seeing with a very high resolution system, which enables you to see the ring systems of the other giant planets. As for example, if you see the image which has come out of the James Webb Telescope, Neptune's rings which have come out magnificently. Now, this is one attempt which I did to classify the different members of the solar system with a Venn diagram, and I found that the work is very difficult because not necessarily you can fit in everything within the framework of the Venn diagram. Let us try understanding this figure. The dark blue rectangle which you are seeing here, it represents everything in the solar system. And there is one light blue color of rectangle which is inside the dark blue rectangle. This light blue rectangle represents the members of the solar system, those orbit around the sun. And here, what is the left out region? The left out region is the region where the members of the solar system which are not rotating around the sun, orbiting around the sun. What could be those? They could be some interplanetary dust which are not necessarily orbiting around the sun. Now let's concentrate within this light blue color box. So here I have written those orbit around the sun, they are called minor planets, but not all of them inside this light blue box are called minor planets. Here it is written except the full-fledged planets and comets. Let us see what are those. There are two circles which I have drawn which represent two sets. The orange color circle which represents the set of massive and spherical objects in the solar system. Any object in the solar system had a tendency to gravitate and self-gravitate and become a sphere. Okay, and if they are very much massive, they are more perfect spheres. That is the understanding. And the light green circle is the set which is the only dominant object in the orbit. So what does it mean? You have sun and you have suppose one member of the solar system rotating around the sun. In this same orbit, if that object is the only big object, then only they will belong to this particular set, green color set. What I mean is, tomorrow if you find in the orbit of Earth, another Earth is coming, another Earth, same size, similar size, has joined our original Earth around the sun, then there will be a big problem because Earth will no longer be in this set. So the only dominant object is only massive, only significant object in its orbit around the sun. Now you see these two sets have overlapped in one region, and in this overlap region reside the full-fledged planets. And we are having 8 known planets today in the solar system. Pluto was demoted in 2006 because of the presence of Charon. It was almost comparable with its size, sharing the orbit around the sun with Pluto, and that's how it was considered as a dwarf planet, which are massive, spherical, but they are not the dominant object in the planet. So Pluto went somewhere here. And here in this region, there are asteroids, centaurs, and any other icy objects. Comets are basically the dirty ice balls. And there is also another classification in the solar system, which are known as small solar system bodies, SSSB. Small solar system bodies are defined as bodies which are neither a planet, nor a dwarf planet, nor a natural satellite. It includes the comets, the classical asteroids, the Trojans, centaurs, and trans-Neptunian objects. Trans-Neptunian objects are the objects in the solar system which are beyond the orbit of the Neptune. So we could have delved in this slide for longer. We will not do so because we have to tell a few more interesting things. But let me tell you, you must have noticed I am emphasizing much on the solar system and how these things are studied, different solar system objects and solar system processes. And let me tell you, whatever I am going to tell, it not necessarily valid only to the solar system, but also the space which is outside the solar system or even beyond our galaxy. So there are 3 different techniques by which we study the space or do space science. One is observation, another one is modeling, another one is simulation. So when we say observation, it is about one way to do observation is the space-based observation. We send satellites, we send space probes, that is a space-based observation. Then we have ground-based studies, and another kind of observation is the observation of the samples. And when I speak about the observation of samples, I speak about the sample return missions. You know, many space missions have returned samples from the moon. That is one example. Or meteor samples, which have come there in their own way, and we are able to analyze them. That is one kind of observation. There is another kind of space study which is done by modeling. Modeling is all about writing the equations of physics from the first principles and trying to explain certain physical phenomena, certain observation which you are able to see either through space-based observation or ground-based or observation of samples. And there are modeling which are not necessarily based on physics-based. Nowadays, another kind of modeling is becoming prominent, which is known as big data analytics-based method based on artificial intelligence, machine learning. And there is another technique called simulation, wherein your model can lead to a computer simulation, wherein in computer you can see how things are happening as things happen in space. In reality, you're creating a virtual environment with the help of a computer software, either with the physics-based equations or artificial intelligence machine learning models. That is computer simulation. Yet there is another kind of simulation which happens, which is known as the laboratory simulation, wherein you create an environment artificially mimicking a kind of space environment. And you perform an experiment in that artificial environment to see what happens. So this is sim. And let me tell you, observation, modeling, and simulation, they form a continuous process. They are not isolated. And observations help modeling. Modeling helps simulation. Modeling simulation also help together to constrain the models, constrain the observations, and constrain the models. So this is how this whole thing moves as a process. And when you are going to do space science and introduction to space science, space science is not only about looking at sky with a telescope or sending a satellite. All these things come to picture as a totality. Now, coming to space observation techniques, there are several techniques starting from the ground-based observations. Here I have shown you a few instruments like SODAR, wherein you send some sound waves and get the reflector sound waves and try to get some inference. You have different towers of the very lofty towers, and here you have instruments mounted on the towers. You are also having different kinds of um, like, gauges like rain gauges or radio waves, multi-wavelength radiometers or weather radars, lidars to probe the near Earth space and decipher certain some information. But these things have got certain limitations. You may like to access the space, not necessarily sitting at the ground, but going to the space, and there scientific balloons become handy. But scientific balloons also come with certain limitations. Scientific balloons, because of the presence of buoyancy, they are not able to go beyond an altitude around, say, 40 kilometers, typically. But balloons have an advantage that they can stay at a certain altitude. But if you have to probe a certain altitude deeper in space, you may have to take the help of what we call the sounding rockets. And sounding rockets, they go, depending on the capability of the rocket, it can go to, say, 80 kilometers, 100 kilometers, or a few hundreds kilometers. But sounding rockets also come with a limitation. Sounding rockets can carry scientific instruments, but sounding rockets cannot launch a satellite. They can carry certain instruments and they can do some measurements about space, but the time they take for or time they get for the scientific observation is very limited, which is not like a satellite or any space probe. And hence satellite space probes are another, which is considered as the best way of studying the space or accessing the space. Now, after having said this, let me tell you about the merits of the space-based observations. See, when you go for the space-based observations, you are going outside the atmosphere of the Earth. So all these effects, which are due to either the absorption of some electromagnetic radiation by the atmosphere of the Earth, that is not happening, or the scattering phenomena, which is very much characteristic to the polluted regions, that is not happening. Or if you are observing some phenomena in space sitting beyond the magnetosphere, well and good, you are in a position to study the charged particles from the sun, let us say. Okay, that's how you are going to get out of the disturbance which are faced by the ground-based observation systems when you are in the space-based observation system. And there are certain special kind of orbits, special kinds of observation points, which are offering different, unique, and special advantages compared to other observation points. Like if you see the sun and the Earth system, there are 5 hypothetical points where the gravitation becomes a state of equilibrium. Whether they are states of stable equilibrium or unstable equilibrium, I'm not going to that discussion. Let me tell you about L1. L1 is a region between two massive bodies where the gravitational forces between two big bodies can cancel out. So it is a case of stable equilibrium. So if you have an orbit here around this L1 point, this orbit is well beyond the Earth's magnetic field, and it is a region which moves along the Sun-Earth line. So if Earth rotates, this point also will rotate. So it is a continuous, if you want to view the Sun continuously without being obscured by Earth or anything else, you will be able to do a lot of solar science from this point. And this is the region where many of the solar observatories, including India's own Aditya L1 solar observatory, sits. So these are certain examples. Or if you see L2, another Lagrange point, wherein you are not going to get sunlight. And this kind of point is very much useful for doing astronomical observations, wherein you want to have a dark sky. You don't want to get baffled by solar radiation. So we can go on discussing about lots of advantages of space-based observations. And in this course, we can also go on discussing different kinds of orbits or different special kinds of mission designs, special kinds of vantage points. Vantage points means strategic points of observation. And after having discussed this, let us discuss about different platforms for space-based exploration. This satellite is a platform for observation. Whenever you are sending a lander, suppose you want to land on Moon or land on Mars, this lander is also a platform. It can carry certain scientific instruments. Or suppose landing is not enough, you want to roam around the landing location. You should have a rover. And suppose there are another kind of mission which is known as flyby missions, wherein your destination is some other planet, but while you are going, you are passing by some other celestial object and studying that in course of the journey to that other planet. So these kinds of missions are called flyby missions. I have also already spoken about this space observatory, which is one example is solar observatories, which is situated at the Sun or first Lagrange point. India's Aditya L1 is one example. Another observatory could be the AstroSat, India's own AstroSat satellite, which is, it is a earthbound orbit, but it looks at sky in deep space. So that is also an observatory. Many of you are aware of that Ingenuity helicopter, which was sent on Mars, and it did some scientific observations. And this is also considered as another kind of platform for scientific observation. And what is present on these platforms, what is present in satellite, what is present in lander, what is present in rover or in observatory, we have scientific instruments. The scientific instruments are magical because they complement and supplement our sense organs. They can study some signal which our human organs cannot study. And these exploration techniques are also divided into two broad categories. One is remote sensing techniques, another one is in situ studies or in situ techniques. In the remote sensing techniques, what happens? You are not directly meddling with the celestial body which you want to study. Something is coming out of that body, you're studying that and getting an inference made of the celestial body. Suppose some electromagnetic radiation is coming out of the celestial body. You are studying that. Studying the electromagnetic radiation, you are making some inference. That is an example of remote sensing. But in remote sensing also, there are two types of remote sensing. One is passive remote sensing, and another one is active remote sensing. In passive remote sensing, what you do, you are satisfied with whatever information is coming from the celestial body, and you're analyzing that, you are making sense of the scientific observations. In active remote sensing, you carry a source of some electromagnetic wave or some signal which you shine on the celestial body you want to study. And the signal which is reflected or scattered back, you are studying that information to draw some inference about the celestial body of your interest. And this is a controlled process of trying to know about the celestial body, which has got definitely certain advantages. And this is called the active remote sensing. Other than remote sensing, you have techniques like in situ studies. In situ, as the name suggests, at site. That is, your technique is meddling with or interfering with or in physical contact with the body which you want to study. One or two examples we can cite. Suppose you want to study the seismicity on the moon. So what you should have a seismometer. You should have the seismometer mounted on the surface of the moon. And when the ground of the moon vibrates, your seismometer records some signals. That is an example of in situ observation. Or if you are having some charged particle detector located at, suppose, fast sun Earth Lagrange point, and these charged particles are coming from sun. They're right falling on your instrument, and your instrument is measuring them. It is an in situ observation of the charged particles. Okay, I can go on citing examples on different techniques, but that is not the objective of today's lecture. But this is to give you a feeling that these techniques to explore the space are basically broadly classified into two classes, remote sensing and in situ, which are placed on the platforms for study. And the science missions are planned following a certain set of steps. See, today when you see a mission has gone to study the Mars or study Venus or study the Moon, how do we know that we have to send a mission to Venus or a mission to Moon? Who told us? It is not always exploration for the sake of exploration. So what happens? You start from a fundamental question about, say, let us take an example of the solar system. And you split this fundamental question to a set of specific questions and set your target. And when you are dealing with your semi-fundamental questions, specific questions, that itself will tell you whether you should study Moon or Venus or Mercury. That depends on the basic problem you want to study. Some problems will indicate that you should study Mercury. Some problems will indicate that you should study Mars and not Venus. And that is the meaning of this statement, set your target. After having set your target, you identify the domains. By domains, you mean whether you want to study the surface or the interior or the atmosphere, if there is any atmosphere of the target body. And then you identify the parameters which you want to study. And after having identified the parameters, specify the ranges and identify suitable techniques to study. I've just spoken about the techniques. Then you come to a definition of the scientific payloads or the scientific instruments which you want to use for the study. And then you define what kind of orbit and what kind of exploration platform you should have to perform this kind of a study. And then you have a detailed observation plan, the ground stations, and that's how an entire science mission is defined. Now, before I conclude, let me tell you, solar system is only a member of our Milky Way. We are just in one arm, local or the Orion arm of the very big Milky Way, and there are different members like Milky Way. Milky Way is not the only one. There are other galaxies also, and there are different other solar systems beyond our solar system, and there are other planets. They are called exoplanets. These exoplanets are also very much prospective because scientists are thinking there is a possibility of finding signatures of life somewhere in some exoplanet. There could be signs of life, there could be signs of even intelligence. So there are different categories. So one category is the gas giants kinds of exoplanets. There are also another category like Neptune-like exoplanets, which is similar to the size of Neptune and Uranus in our solar system. There are super Earths, which are larger than Earth, smaller than Neptune, and also the terrestrial and Earth analog kind of exoplanets. And we speak about habitability, sign of life, and intelligence, extraterrestrial intelligence. And space is not only about growing in space. There is another aspect which I will tell before I conclude, maybe in another 5 to 6 minutes. If you go step by step, we have started with our Earth, then we have discussed about the solar system. Then we have also discussed about star system when we have talked about Sun Earth system, which is about star system when I speak in more general terms. And then different star systems can form clusters or globular cluster and stellar association. They form a galaxy. Multiple galaxies form galaxy groups. Still going to the bigger level, galaxy cluster, still growing, taking several of them together, supercluster, then galaxy filament, then observable universe. And beyond the observable universe, there could be something unobserved yet. We call it as the universe. Today we speak about a universe of about 93 billion light years in diameter. And what you can see in this picture, small dot at the center of this circle, while the entire circle represents the limit of the observable universe. Small center, it represents the Virgo supercluster, which is the home of the Milky Way. It's just a dot here. And our solar system is just a member at one edge of the Milky Way. So now space, I tried giving you a perspective growing in volume, growing in space, but that is not the entire picture. It is also about growing bigger in time. And when I speak about going bigger in time, many of you must be very familiar with this picture. People speak about the Big Bang, which is the initial trigger of today's formation of cosmos and evolution, which have happened for the last around say 14 billion years from now. And today we are here, and the arrow of time moved from my right side to the left, from my left hand side to the right hand side. And if you see, about 4.5 billion years ago, the solar and the planetary solar system was formed, and there was a time when stars and galaxies were formed, still uh, before the formation of the solar system. And there was a time when there were no star, no galaxy. It's very interesting. Today we speak about the solar and planetary science because sun was there, planets were there. Today we speak about astronomy and astrophysics because stars are there, galaxies are there. But what about when there was no star, no galaxy? That is the realm of cosmology. So what happens if you have to summarize after the Big Bang, say after around less than 10 to the power minus 43 seconds of the Big Bang, which we call the Planck epoch, our first understanding of the physics starts from there. Anything towards the Big Bang, starting from the Planck's epoch, we say it is the regime of singularity where the laws of physics do not work. And it is the time when all the four fundamental forces, the gravity, electromagnetism, weak nuclear, and the strong nuclear forces, they have started unifying. And inflation happened. You see here, all of a sudden, how this radius has started increasing. And this is a period of extremely rapid expansion of the universe. And this expansion has smoothed out the universe and it became a bit uniform. And then started a few minutes after the Big Bang, the process of nucleosynthesis, wherein the neutrons and protons, they started combining and temperature was conducive enough, cool enough for this merger to happen, and light elements like hydrogen and helium started forming. And then came the era of, we call recombination, around say 3.7 lakhs of years after the Big Bang, where universe cooled enough for the electrons and protons to combine, forming neutral atoms. And this made the universe transparent and allowing the photons to travel freely, and which we observe today as the cosmic microwave background radiation, which we call the CMB radiation. And then there was a period of the time when, even before the formation of the first stars, which happened much later, we call the dark ages. Dark is a term which represents no light. And this dark ages of the universe was filled with neutral hydrogen and helium. And then the formation of the stars and galaxies and this gravitation played a very important role to cause clumping of the matter, and which led to the formation of the first stars and the first galaxies. And then we had our subject of astronomy, astrophysics. And these early stars and galaxies started emitting lights. And this, a part of this light, which were energetic enough, caused ionization of the hydrogen. And today, when we are speaking, the universe continues to expand, which is driven by many factors. One is dark energy, people say, and somebody says that no, there are multiple big bangs happening, which are different stories altogether. And galaxies continue to evolve, and new stars or planets are still forming. So, universe is not only about space, but also about the time. Maybe I will wind up in another 5 minutes. Before I wind up, I would like to tell you something very interesting. See, when I told you about the cosmological timeline and space science is not only about space, space science is also about the science of time. I also must tell you about the different techniques which are present day scientists use for probing the different cosmological timescales. Say when you speak about the early universe information comes from antennas like LISA. You know, LISA is the laser interferometer space antenna, which detects the gravitational waves, not the electromagnetic waves. What are gravitational waves? Like if you have a charged particle and you make it accelerate, it will cause electromagnetic radiation. Similarly, if you have a mass and if you make a mass accelerate, then it creates a ripple in the space-time continuum, and that is propagated as what we called a gravitational waves. And MWA is nothing but the Murchison White Field Array. So there are different kinds of uh, physical phenomena which are addressed by different kinds of systems like expansion rate and structure, LISA does, and radio telescope like LOFAR. LOFAR stands for the low frequency array. They also address these kinds of different parts of the evolution, the cosmological evolution, are addressed by different instruments today. So we have to appreciate technology was not that much mature till a few decades back. Now, all of a sudden, we have become mature technology-wise and started probing the universe to a great extent, even to the extent of early universe. And also, we also have to appreciate one thing. Information today about the universe is not only coming from the electromagnetic waves. Electromagnetic wave of light is only one messenger. Information is also coming from the gravitational waves. Information is also coming from the neutrinos. Information is coming also from the cosmic rays. And leave alone gravitational waves, leave alone neutrinos, leave alone cosmic rays. In the electromagnetic radiation itself, there are different parameters like whether the blinking is happening, which we call timing, or what are the wavelengths which are constituting the electromagnetic wave, which we call spectroscopy, or the polarization of the electromagnetic wave, and combining with this the imaging of a celestial body. All these are different facets of understanding the universe with electromagnetic radiation only. And this approach is called multi-messenger astronomy. So let us not get locked to the idea that only electromagnetic radiation is used to understand different celestial bodies of the processes. So I conclude with these slides. Pictorially, I am summarizing different realms and different techniques of space science have been discussed. And we have discussed about the rules of modeling, simulation, and observation, ground and space-based observation. Also, I have discussed about different techniques, remote sensing and in situ. I have also discussed about how to access the space with balloons and rockets, platforms, and also spoken about the multi-messenger approach in doing space science. And today, there are four major verticals: astronomy, astrophysics, cosmology is one vertical of space science, heliophysics and space weather is yet another vertical of the space science. Solar system is yet another subject, and near Earth space astronomy, aeronomy. Aeronomy is the study of the upper atmosphere. Ionosphere, thermosphere, magnetosphere system, or the near Earth space in total is yet another particle. So with these, let me conclude here, and I will be happy to take a few questions maybe for another 5 minutes. Thank you very much.